All right, this is your 4.3 lesson lecture. Today we are going to talk about fission and fusion. So fission is the first one we're going to touch base on, and it is the splitting of a nucleus into two or more similar nuclei. So neutrons are fired at a large nuclei in a nuclear reactor, and then 2 to 3 neutrons are released when that nuclei splits, which can then split into other nuclei. So as you see there, Ms. Laporte is kind of pointing that out there. So that one neutron is being fired at to a larger nucleus, and it is creating and spitting out 2 or 3 more neutrons. Okay, this is creating a chain reaction, which we're going to show you a little simulation here. So as you can see, as those neutrons are getting fired out of there, they are going and touching other nuclei, which is then causing that chain reaction.
Sorry, Case, I'm just going to scroll back to the beginning just so we can see.
Perfect.
Starting out there. As you have that first neutron hit and you see a splitting, and then we have those neutrons that are released. So now each of these neutrons are going to go and they are going to split another nucleus. Case normally would draw like, I don't know, what do you do, like the secrets or like telephone kind of thing, where she draw that on the board, like one person tells a secret, they tell 3 people, and then those 3 people tell somebody else. And so you have this chain reaction, right? This amplification. And so that's what you're seeing as those neutrons then float away and come into contact. So way more neutrons are present, lots of splitting, and we have a new radioactive element that are left over after we have divided that original larger nucleus. All right, sorry, Casey.
Oh, good.
Oh, I gotta do the thing. Hold on. Bing.
Okay. No worries. All right. So a huge amount of energy is then produced from this and can result in things like the atomic bomb. Okay, so these are atomic bomb-like. I don't remember. Oh, and then it does create radioactive waste. So as a result of fission, it does create radioactive waste.
And so what you saw, some of that radioactive waste was some of those byproducts, all right? And what that means is that you have leftover elements that are still radioactive, but we can't really use them for stuff. And so we just have to kind of stockpile them, put them in lead-lined containers, and then it's like, what do we do with all this junk, right? We're left with all this stuff. So that's one of the pitfalls in nuclear energy when we use fission.
Yep, so definitely have fission and have that keyword of splitting be your keyword. So splitting and fission together. Okay. And the next one is fusion. Okay, so fusion is the joining of 2 small nuclei to form a larger nucleus. These particles and energy are released here. And this is how stars, like our sun, are powered. Okay, so the word sun is highlighted there. And the way that we like to kind of give you as a reminder that fusion has to do with the sun is that they both have U's, the letter U. So fusion is taking place in the sun, and that is where they're joining together. Okay, so an example of this are thermonuclear bombs. Those also have fusion. It requires extremely high temperatures. So think about your hottest temperature you've ever been in, and this is a way more than that, so 180 million degrees Fahrenheit. It produces less radioactive waste and energy production, and this could be unlimited if we could figure out how to create that here, which, because of that temperature, is going to have to create some new types of products in order to contain that type of heat here on Earth.
Yes, they would. So when we talk about nuclear uses of nuclear energy, one of the primary ways in which we use nuclear energy is through nuclear power plants. So you may have seen stacks like this that are around. We do have a few in Illinois, and maybe on your travels elsewhere on road trips, you may have seen some. When you are looking at a nuclear power plant, what you are witnessing, without actually seeing it, is the controlled fission. So that was the first example that Ms. Case talked about, fission, where we're taking a large nucleus and splitting it into two smaller ones. So that's the one that's going to produce that radioactive waste, right? Basically what happens is the reaction, so that splitting of that large nucleus into two smaller ones releases heat, all right? And that heat is warm enough to heat up water, and that produces steam. And then what that results then is in turbines, kind of think of like a pinwheel, right? Larger, we think of wind turbines. You may have seen those that are out in the fields, but they are spun, and they are going to convert that nuclear energy into heat, that heat into mechanical, which is the moving of that turbine, and then that mechanical energy is then converting into electricity that we use to power homes and businesses and buildings and things like that, right? What's really great about nuclear fission power plants is that a very, very tiny amount of this uranium-235 can power a huge amount of space for a huge amount of time, much more so than traditional fossil fuels like gas and coal and things like that can power. But again, that downside is that A, we don't have a lot of uranium-235, meaning it's in limited quantities, and it produces that radioactive waste, which is not the greatest, and we don't have a way to dispose of it safely. It just kind of sits for eternity. So not the best. That's why, like Ms. Case said, it would be really great if we could manufacture, create, figure out how to run nuclear fusion, all right, taking two smaller nuclei and pushing them into make a larger nucleus. If we could figure out how to do that here on our planet safely, that would be huge, because you don't get that radioactive waste in that process. And the amount of energy that could be created through that, obviously, as we see in the huge number of stars in the sky, is significantly higher than any other way in which we are currently creating and reusing energy on Earth. So nuclear power is probably the most familiar type of use for nuclear energy. The second would probably be nuclear weapons, which is not the greatest. In atomic bombs, like Ms. Case already mentioned, that is where you are going to see fission, so those chain reactions that we saw, but it's uncontrolled. So notice the keywords in green there. For nuclear power, it says controlled fission of uranium-235. For nuclear weapons, it's uncontrolled. And the purpose being is that we're not trying to limit, we're not trying to narrow down the heat and energy released. We want as much as possible. And that's what happens in an atomic bomb, and that's why the results of releasing and dropping atomic bombs can be so devastating, as was seen near the end of World War II in Japan, and frankly are still being seen in ramifications not only to those people, but their descendants past that point. The other type of nuclear weapon are thermonuclear, sometimes referred to as hydrogen bombs. And those bombs are even more powerful and can be more devastating. You can see there, 100 times more devastating than a typical, if you will, nuclear bomb. And that's because it uses the energy and heat and power created from that fission reaction, from that chain reaction, to induce high enough temperatures to cause fusion to happen. All right, so basically what we do is we create that fission, we have that chain reaction, and the temperature gets so hot inside the bomb that it is able to then take those smaller nuclei and smash them together and have fusion, just like what's happening in the sun. So those super high temperatures that Ms. Case mentioned are what's going to happen when we have a thermonuclear bomb. So you can imagine the amount of devastation, long-lasting effects, cancers, other diseases that could happen to any type of life, and especially humans, if we were to use that type of nuclear weapon. Which is why there are lots of laws and agreements by different nations about how we use nuclear weapons, where we store them, etc. The other main use of nuclear energy and nuclear power is through in medicine. This is probably the most common way in which we use nuclear energy, and you're just not aware of it. But there are a couple key ways in which we use that nuclear energy. One is through radioactive tracers. And basically, these are radioactive isotopes that are injected into a patient, usually before some type of scan or procedure. so that different parts of their body can be located and seen better in the scan. There's a really cool video that we recommend you taking a peek at if you were to get a PET scan. There are radioactive isotopes. One of them that I can think of off the top of my head would be iodine, because that's something that's going to bind to DNA. And it allows scientists and doctors to be able to track different aspects of those body parts, including your DNA. The other way in which we use nuclear energy in medical purposes is through radiation therapy. So when patients get radiation, what they are receiving is high energy X-rays that are targeting specific areas in the body that are uncontrollably growing, like cancerous cells or fast dividing cells. So like your skin and your hair and things like that. And the purpose of those targeting radioactive isotopes is to make, and that radiation is to make sure that those uncontrolled cells stop dividing. And again, there is a quick little video that discusses how radiation works in terms of therapies for cancer patients, as well as other conditions that might need that type of therapy.